Boleh doktor.
Okay. Thank you for the response. Okay, so yesterday we have covered on the chapter 2, but on the last section, which is Poisson's ratio, which is haven't have time to cover. So I will just proceed with the last section or now. Siapa yang masuk ni? Okay. So I will just go for today's lecture. Continue probably just a few minutes, and after that we end the lecture and then continue with the tutorial question. Sekejap, ada orang di lobby ke? Ada. Okay, so here is Poisson's ratio. What is Poisson's ratio? Is the ratio of lateral contraction strain to longitudinal extension strain in the directions of stretching force. So for example, we have this component of lateral strain at the y-axis, right? Lateral strain at y-axis compressed to this material, and then these two sides on the longitudinal strain is on the x-axis. So this part, when they have a compression force applied to this material, this is what we call as a lateral strain. Okay, meaning that the size is reducing. But if we have a longitudinal strain, it stretch this material. So we call this as a longitudinal strain where the length has increased. So in the Poisson's ratio is the ratio between the lateral strain divided by longitudinal strain. And the sign convention for Poisson's ratio is we apply as a negative sign. So lateral divided by longitudinal strain is called as a Poisson's ratio. So for the symbol for this Poisson's ratio, we call the symbol of nu. Okay, nu, such as V, the V shape, but this is like Romans call it as a nu, right? So nu equals to minus epsilon lateral divided by epsilon longitudinal. Epsilon is strain, okay, symbol for strain. So strain for lateral divided by strain longitudinal. So this is like the axis. So in the short form, nu is the Poisson's ratio equals to minus epsilon y divided by epsilon x. Epsilon y is in the y-axis and epsilon x is in the longitudinal in the x-axis. So the unit for Poisson's ratio is no units. Okay, so here is we have some direct tutorial question. Okay, a prismatic bar with circular, means round, circular with the diameter of 30 mm. Okay, subject to tensile force of 85 kilonewton. Okay, tensile means is stretching. This item or prismatic bar is stretched with 85 kilonewton loads. The bar has a length of 3 meter length, and diameter is 30 mm, made of aluminium with elastic modulus of 70 kilonewton per millimeter square. Okay, and Poisson's ratio is 1/3. Calculate the elongation, okay, the delta and diameter of reduction. Okay, meaning that this lateral strain as well as the longitudinal strain. We have to calculate. So assuming stress at the limit of proportion is 180 kilonewton per mm square. So the stress is sigma equals to 180 kilonewton per mm square. So you just take out all the information from this question. Okay, the force, the stress force, the stress value, and then the diameter, the length of this bar, and then the okay, sekejap, saya dah masuk tadi here. Okay, so here you already has everything. So what you need to do is to just cutting at the mid section of this prism bar. Okay, so we have this inside force is Fx, okay, in the x direction, Fx. So this is outside force, 85 kilonewton. So the inside force will be Fx. So the Fx is, because it's in equilibrium, okay, for example, you have taken to the right side of that side is positive. So this is actually equals to 85 kilonewton or 85,000 Newton. Okay. So the area, because this is circular shape, so you apply the same formula for circular shape area, which is pi r squared or pi d squared over 4. So you just put all the value inside this diameter, which is already given in the question. Okay, it's the t squared over 4, and then this is force due to the Fx direction, the internal force. So you'll get the stress value for this prismatic bar is equals to 120.3 Newton per mm square. And then the axial strain at the bar is, you use the modulus of elasticity equation, which is E equals to sigma divided by epsilon. Okay, from here you can have the directly get the value for the strain of this E epsilon x is actually longitudinal strain. So the longitudinal strain equals to sigma divided by E. Sigma is from here 120.3 Newton per mm square divided by the, because it's aluminium, so you have to check, I think from the question got, or you can get it from the table. If the question provide you the value, so you just put on the value. So here the sigma divided by the modulus of elasticity is equals to 0.0017 to no units. So this is the axial strain at the longitudinal axis. So the total elongation is this one. Because of delta is the change of length, okay, the change of length divided by the total length or the original length equals to the epsilon. So you rearrange the equation for the strain, which is epsilon equals to the elongation divided by original length. So this is, you rearrange the equation, so you'll get this delta. Okay, delta is the total elongation equals to sigma x. Okay, epsilon x is the strain at the longitudinal side times with the total length of the prismatic bar. So this is the value of epsilon, and this is for the total length of the prismatic bar. So the total equation at the longitudinal strain is equals to 5.16 millimeter, right? Okay, you already got the total elongation. Okay, elongation and diameter reduction. Now you need to calculate for the diameter reduction. Okay, from the question of Poisson ratio, nu equals to minus epsilon lateral divided by epsilon longitudinal. Okay, this is already calculated, okay, previously. Because this is nu already given from the question, which is equals to 1/3, right? So you just rearrange the equation. The nu, this one, this is what you need to calculate. You need to figure out how is what is the value for the epsilon lateral. So rearrange this equation. So we'll get this epsilon y equals to minus nu times epsilon x. So this one equals to minus 1/3 is the Poisson's ratio times the epsilon x, which we have calculated earlier. So this is the value of the uh, epsilon lateral, which is minus 0.000057. But what the question need you to do is to get the reduction in diameter. So from the equation of strain, okay, strain equals to total change in length or change in diameter divided by L. Okay, L is the original length. So the diameter reduction, this is what you need to get. Okay, this delta is actually same symbol as delta D, right? Meaning this one is for the diameter reduction, shortened in Y direction. So rearrange this equation, so we'll get this delta D for the diameter reduction equals to epsilon Y times D. So this is equals to, because epsilon y here, what we have calculated is this minus, okay, because it's reduced in size, we have reduction in size, which is the sign will be minus, times the total diameter of the prismatic bar, okay, which is 30 mm. So just times these two values, you'll get the reduction diameter is equals to 0.0171 millimeter. Okay, so that's all for the section on the Poisson's ratio. Do you have any question? If you don't have any questions, so you can put thumbs up or clap your hand. Thumbs up if you understand. Right, very good. Okay, it's quite direct. One question. Okay, now we move to the tutorial question that I provided you yesterday. So this is already we covered and we discussed during the class. Okay, so no need to repeat it again. Okay, so this is the second question from the class yesterday. So this is the question about aluminium tube. Okay, a circular aluminium tube with a length of L equals to 420 mm. Okay, is loaded in compression. Okay, this is the forces, and this is the total length of this aluminium. The hollow segment, okay, this is the area of the hollow segment. This is solid, but there are some part that as a hollow. It's not solid. Where they have this hollow section has a outer diameter is 60 mm, and then inner diameter is 35 mm. And then the solid segment has a length of 2/3. Okay, 2/3. Okay, total length of the solid segment over here to here is 2/3. Has a diameter of 60 mm. So a strain gauge is placed on the outside of the hollow segment. Okay, this is the strain gauge to measure normal strains in the longitudinal direction. So from the question is A, if the measured strain in the hollow segment is, okay, epsilon h is for the strain values for the hollow segment. Okay, hollow segment is equals to this 470 times 10 to the power minus 6. And what is strain of epsilon at the solid segment? Means over here, what is the value for the strain at the solid segment? Hint, the strain in the solid segment is equal to that in the hollow segment multiplied by the ratio of the area of the hollow to that of the solid segment. So you need, when you do the calculation on this, so you have to follow this guide to answer this question. First of all, you have to take out all the information. The length, the total length of this circular aluminium tube is 420. D2 is the outer diameter for the hollow section, and D1 is for the inner diameter for the hollow section. And already given to you the strain for hollow section is 470, and then uh, the stress value is 48 megapascal for the aluminium. So part A question, so you have to know what is the diameter, the area, okay, the area for the solid segment and then for the hollow segment. For the solid segment, you can get the diameter area because it's already given to you the diameter, right? So 60 diameter is the for the solid segment. And then for the hollow segment, because they have gut hole at the center of this segment, so you have to minus the outer diameter with the inner diameter. So this question will be used for the hollow section. So the area is for the hollow section is this one. Okay, and then this is for the solid section. Now to get this epsilon hollow, okay, because in here mention about solid segment is equal. Okay, this one is equals to EH multiply, means that the solid segment equals to the hollow segment multiply with the area ratio between the hollow divided by solid. So this one equals to the area AH divided by the AS times the epsilon H. Okay, from here, you already determine the AH hollow area and then the solid area. And then you have this already provided to you in the question. So you just put all the value inside this equation. You get the epsilon or strain at the hollow section is equals to this 3.1001 times 10 to power minus 4. Ya, ada soalan? Lepas tadi tu. Right. So we have already answered for the question A. Now for question B, what is the overall shortening delta of the bar? So we have to determine the shortening of the bar. So by using the equation of strain, okay, this delta equals to epsilon times the length of the hollow section, right? So the delta equals to epsilon. Okay, this is the length for hollow section times with the solid section. This is the length for the solid section. This is the length for the hollow section. So you just put on the value. Okay, the L value is already given, right? 420. Here is for the 420, and then this 2L is coming from here. So all the value is already given. So you just put all the value for this already calculated, this already calculated. So the shortening, okay, this total shortening for this hollow and the solid bar is equals to 0.1526 millimeter. Okay, if we separately calculate each of these hollow and solid bar, the shortening for the hollow section is 0.066, and then shortening for the solid bar is 0.087 mm. So this one plus this one, it will be equals to this. Okay, so the last question is see if the compressive stress in the bar cannot exceed 48 megapascal. Okay, meaning that the sigma is not exceed 48 megapascal. What is the maximum permissible value of the load? Okay, so from here we have two areas, right? So we have this solid area and then we have this hollow area. So has different meaning with that we have to get two types of force, okay, permissible value of load P. Okay, for the hollow part, the P load P maximum for the hollow part, okay, which is from the stress equation, sigma equals to force divided by A. You rearrange. So from that, you get the P equals to sigma A. Okay, sigma A is for the stress aluminium, 48 megapascal. times AH. This is the area for the hollow. So we'll get the hollow section, the force applied for the hollow section is equals to this, 89.535 kilonewton. For the solid section, so the sigma aluminium times the area for the solid part, so you get the 135.717 kilonewton. So you use this one can use for this segment or for this aluminium tube, but for the controls value for the factor of safety, so you have to get that the maximum can apply, the loads can apply to this aluminium tube is 89.535 kilonewton, even though this is the highest one. But for the safety of factor, you have to control the value that the maximum should be provided as minimum as possible, which is compared to this one. So you have to use the lesser value, which is 89.535 kilonewton. Okay, paham? Thumbs up kalau paham. Alright. Oh, Max Leander. So what you want to ask? Siapa tadi kat tangan?
Tidak. Saya tekan.
Okay. Right. Okay. Alright. This one is the second question. This is what you need to do, is to plot in the graph. Okay, plot in the graph paper. So here, the question asks you a specimen of a metacrylate plastics is stays in tension at room temperature. Okay, this is the plastic material producing the stress strain data listed in this table. So what you need to do is to plot the stress strain curve, okay, in the graph paper and determine the proportional limit, modulus of elasticity, which is the slope of the initial part of the stress strain curve, and the yield stress at 0.2% offset. Is the material ductile or brittle? So two questions here you need to do is, first is to determine the stress and strain curve, right? So here is the curve for the tiga question. So first is the plot. So after you plot this table into the graph paper, this axis for stress, so the unit is megapascal, and then the strain in the x-axis, no unit. So here have each point, so you have to put all the values inside lah, which is 0, 8, 7.5, okay, 2.25. So it can be like simplified like this: 0, 20, 40, 60, or 0, 10, 20, 30, 40. Okay. And then this part, the smallest one is 0.0032, and then the highest value is, tak nampak kan? Kat bawah sekali tu ada tu kan? 0.04 ada lagi, before its rupture over here. So if you plot here, you use this, you can use 0.01, okay, 0.02, 0.03, 0.04, okay, until 0.06. So if plot, and then you draw the line for each of these points, so you will get this point of curve. Okay, this curve until it's break. So this is the point of fracture. So complete for the question on the plotting the curve. Now you have to determine the proportional limit and modulus of elasticity. So the proportional limit is sigma PL, proportional limit. Okay, proportional limit is equals to how much? You know the meanings, the theory that we have already discussed in class. Proportional limit is what? Right, so the maximum before yield achieve the yield point. So that should be the proportional limit of this material. So before the yield part of proportional limit, so you can just assume that it is close to the curving, meaning maximum the linear part of the curve will end. So which of the point that you can see it is not in straight line. So you just assume that this is between this one. Okay, this is linear curve, linear line, still inelastic. So that this is the maximum part of the where the proportional limit achieved. So it is assumed to be like 47 or 46 or 48. So plus minus. Okay, 47 megapascal. Right, and then for the to calculate the modulus of elasticity, which is E equals to stress divided by strain. So from here, you can just put any triangle. Okay, put any triangle over here. So you have to calculate the 40, okay, 40 megapascal minus 0, and then 0.017 minus 0. So one big triangle over here, one big triangle over here. So we can get the slope, or this one called as a modulus of elasticity, equals to 2.4 gigapascal. So you get this value plus minus lah. If you get the, I think slope, if you put any point, so still you can get this 2.4 gigapascal. Alright. So done for the modulus of elasticity. Now you have to answer this yield stress at 0.2% offset. Meaning that they have offset 0.2%. This one, this curve, you just assume, right? This one, there's no calculation on this, but offset meaning that they are moves into that direction. Okay, move it into the right, at a little bit on the right, 0.2% offset. So you determine on the line. Okay, so if you put the line 0.2% offset, or you can calculate from here, you just add 0.2% from this point, and then also from here, strain value, or you can just assume it is to 0.2% offset. So it gives you one line, okay, one line to the linear shape of this curve, and then it will stop here. When it's linear and then fractured at the point of proportional limits. At linear point, it's already fractured. Okay, meaning that this material is, if we put the offset of 0.2%, means this is a brittle type of material. Okay, because it breaks at the linear point. Okay. So here, comment material is brittle because the strain after the proportional limit is exceeded is relatively small. Okay. Boleh? Boleh faham? Boleh lah. Slow je kan, bagi thumbs up. Alright, so the last question. Okay, the last question. This is on the a tensile test is performed on the brass specimen 10 mm in diameter using a gauge length of 50 mm. So here is a gauge length of 50 mm. When the tensile load P reach value of 20 kilonewton, the distance between the gauge mark has increased 0.122 mm. So here is the point of gauge. And then when we put loads P here, which is 20 kilonewton, and then the distance of this gauge increased by 0.122 mm. So what is the modulus of elasticity E of the brass? Alright, so E, this is all the parameters lah. Okay, normally you just take out all the parameters and then calculate for the modulus of elasticity. So first of all, you have already the loadings. This is the strain value, and then the stress value is you need to calculate first. So the sigma equals to force divided by A. Force applied is 20 kilonewton divided by the area, because this is circular. Okay, circular means diameter is 10 mm. So the area is pi d square divided by 4. So the sigma or the axial stress equals to this one, 254.6 megapascal. Okay, and then calculate for the strain. Okay, the strain value, axial strain, epsilon equals to delta divided by L. Delta from the question is 0.122 divided by the gauge length is 50 mm. So the epsilon or axial strain equals to 0.00244. Okay, from this question, you can have directly get the modulus of elasticity, which is E equals to the stress divided by the strain. The stress is 254.6 divided by strain, and you get the modulus of elasticity is equals to 104 gigapascal. Okay, and then question B, if the diameter decreases by 0.083 mm, what is the Poisson's ratio? Okay, so you have to take out the Poisson's ratio equation, which is nu equals to minus lateral divided by longitudinal. So the delta value, this one is this one, okay, 0.0. What is this? Or this one, okay, the shortening, okay, because the shortening 0.0083. The shortening is 0.83 divided by epsilon times d. This one is we get from the increase in length from this bar. The epsilon, we already got this, okay, because this axial strain 0.00244 times the diameter, okay, the diameter of the bar. Okay, so we get this value, and the Poisson's ratio is equal to 0.34. Okay, this is quite a simple question. You can just put the equation directly to that. You can get directly answer from this question. It's not complex. Okay, supposedly they have some negative sign over here, right? So that this one should be in the form of negative 1. But if we have used the formula that I provided you, if they have negative sign convention, so you have to put the sign convention negative. This one, they don't use the sign convention of negative. So you just put, because it's decreasing means this is negative. Okay, negative, right? So here's supposed to be negative lah over here. All right, okay, so I think that's all for the lecture on the tutorial. You have any question? Okay, so kita boleh habis awal lah ni ya. Okay, so I will share you the link for the attendance today. Sekejap. Attendance. Okay. Chat. Okay. Attendance I've already shared in the text chat box. Okay, if you don't have any questions, so I'll see you next month. Okay, next week at the class, huh? Right. Okay, guys. Thank you. Assalamualaikum.
Thank you, Dokter.
Oke, dokter. Waalaikumsalam. Thank you, dokter.